The humid air of Saipan clung to everything like wet wool. It was mid-July 1944, and the island had just fallen to American forces after 3 weeks of grinding, brutal combat. Amid the wreckage of shattered bunkers and mangled palm trees, a team of Japanese aviation engineers moved carefully through the remnants of Aslito Airfield, now occupied and renamed Isley Field by the victors. They were not soldiers. They were technical specialists from the Koku Gijutsu-sho, the Japanese Navy's air technical arsenal, men trained to dissect, measure, and understand the machinery of war. Their mission was simple in concept, but staggering in implication. Scattered across the cratered runway sat 3 captured American aircraft, prizes taken during the chaotic final days before the island's fall. Among them, resting on its wide landing gear like a predator at rest, was a Republic P-47 Thunderbolt. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The engineers approached cautiously, as though the silent machine might still harbour some threat. Its .850 caliber machine guns jutted from the wings like the fangs of a steel beast. Bullet holes pocked the fuselage, evidence of the firefight that had brought it down. But what drew their attention, what made them pause mid-step, was not the damage, it was the size. The P-47 was enormous. Not just large, but grotesquely, impossibly massive by Japanese standards. It sat nearly 5 meters tall at the tail, its wings spanning over 12 meters, its body thick and muscular in a way no Japanese fighter had ever been. One of the engineers, Lieutenant Hiroshi Tanaka, walked slowly around the cowling, his hand tracing the contours of the armoured nose. He had spent years studying the Mitsubishi A-6M0, the pride of the Imperial Navy, a fighter so light and nimble it could turn inside anything the Allies flew. This was not that. This was something else entirely. The chief engineer, Commander Saburo Nakamura, ordered his men to begin the inspection. They carried notebooks, calipers, micrometers, and a portable camera wrapped in oilcloth to protect it from the tropical moisture. Their first task was to document the exterior, every panel, every rivet, every dimension. They measured the propeller blades. 4 of them, each over 3 meters long, cast in blackened steel and bent slightly at the tips from the force of the crash landing. The spinner alone weighed more than the entire propeller assembly of a Zero. When they pried open the cowling fasteners and swung the massive panels aside, the noise of metal scraping metal echoed across the silent airfield. And then they saw it, the engine. It filled the entire forward section of the fuselage like the heart of some industrial giant. 18 cylinders arranged in 2 rows, each one the size of a man's forearm, wrapped in cooling fins that radiated outward in perfect geometric precision. The cylinder heads gleamed dully in the afternoon light, scorched black in places from exhaust heat, but still intact, still whole. Fuel lines snaked through the compartment like arteries. Oil sumps the size of water jugs sat bolted beneath the crankcase. The supercharger ductwork, thick as a human torso, ran back toward the cockpit, feeding compressed air into the beast's lungs. Nakamura stood frozen, staring. For a moment, he forgot to breathe. This was not an aircraft engine. This was an expression of industrial philosophy so alien, so fundamentally different from everything Japan had built, that it felt less like examining a machine and more like deciphering a message from another world. He had seen American engines before, salvaged Allisons from downed P-42s, a Wright Cyclone pulled from a wrecked B-25. But those had been inline or smaller radials, engines Japan could at least conceptually understand. This was beyond that. Lieutenant Tanaka, standing beside him, whispered the question that had formed in both their minds. "Commander, how much power does this produce?" Nakamura didn't answer immediately. He reached out and placed his hand on one of the cylinder heads. It was still faintly warm, hours after the crash. He thought of the Sakai engine that powered the Zero, 940 horsepower, elegant, efficient, light. The engine had been designed to extract maximum performance from minimal weight, a triumph of Japanese engineering ingenuity. It had dominated the skies in 1942, turning circles around every Allied fighter it faced. But that was 3 years ago. The war had changed. The Americans had changed. And standing before this captured Leviathan, Nakamura understood something that the high command in Tokyo had not yet fully grasped. Japan had been fighting a different kind of war. The engineers spent the next 2 hours carefully photographing the engine from every angle. They sketched the layout of the accessories, the magnetos, the carburetor, the oil pump. They noted the material finish, rough by Japanese standards, almost agricultural in its lack of polish. The castings bore visible mold lines. The bolts were oversized, their threads coarse. Nothing about it was delicate. Nothing about it spoke of the meticulous craftsmanship that defined Japanese aviation. Yet it radiated power. When they finally located the data plate riveted to the engine mount, Tanaka leaned in close, squinting to read the stamped letters through a layer of grime and oil. Pratt & Whitney R 2800 double wasp. Rated output 2000 horsepower. Tanaka blinked. He read it again. Then, a third time, certain he had misread the numbers. 2000. Not 200. Not 1200. 2000 horsepower. He turned to Nakamura, his voice barely audible. Commander, this engine produces more than twice the power of our Sakai. Nakamura nodded slowly, his face pale beneath the tropical sun. More than twice, he repeated. Nearly 2.5 times. The implications settled over them like a weight. The Zero's Sakai engine, at full power, produced 940 horsepower in its early variants, 1130 in the later models. Even Japan's most powerful operational fighter engine, the Homar, struggled to reach 1800 horsepower and was notorious for overheating and mechanical failure. Yet here sat an American engine, mass-produced, reliable enough to power thousands of aircraft, casually outputting 2000 horsepower as though it were a minor engineering detail. Tanaka did the math in his head. 2000 divided by 940. The P-47's engine alone produced as much power as more than 2 Zeros combined, more than 2 complete aircraft. Engines, airframes, everything. The raw mechanical force contained within this single radial motor equaled the total output of an entire flight of Japanese fighters. He looked at Nakamura, his voice shaking slightly. Sir, if this is their standard fighter engine, what are they putting in their bombers? Nakamura had no answer. He simply stared at the double wasp, his mind racing through scenarios, through combat reports, through the growing list of losses that had been mounting in the Pacific over the past year. Suddenly, many of those losses made sense. Suddenly, the reports of American fighters shrugging off damage that would have crippled a Zero, of Thunderbolts diving away from combat at speeds no Japanese pilot could match, of P-47 seconds, climbing back to altitude after ground attack runs, as though the extra weight meant nothing, all of it crystallized into a single, terrible realization. The Americans were not just building more aircraft, they were building fundamentally different aircraft, powered by a philosophy Japan had never needed to consider. Not elegance, not efficiency. Not the razor's edge balance of performance and weight, just brute, unstoppable, industrial power. Commander Nakamura ordered his team to continue the inspection. They would measure everything: the wing structure, the armor plating, the fuel capacity, the armament. Every detail would be documented and sent back to Tokyo for analysis. But even as he gave the orders, even as his men moved methodically through their tasks, Nakamura could not stop staring at that engine. Because he understood, standing there in the wreckage of Saipan, that Japan was not simply losing battles. Japan was losing a contest it had never fully understood it was in. A contest not of skill or courage or tactical brilliance, but of industrial capacity, measured in tons of steel, rivers of oil, and the raw, unyielding mathematics of horsepower. And the P-47's Pratt & Whitney R 2800, sitting silent and inert in the tropical heat, was merely the beginning of that story. To understand why the discovery of the P-47's engine shook Japanese engineers to their core, one must first understand the world in which Japan's aviation industry had been born. It was a world defined not by abundance, but by scarcity. A world where every gram of aluminum, every litre of fuel, every kilowatt of industrial power had to be carefully rationed and precisely allocated. Japan in the 1930s was an island nation with grand ambitions but limited resources. It possessed no domestic oil reserves. Its steel production, though growing, lagged far behind that of the United States or Germany. The raw materials needed to build a modern air force, high-octane gasoline, aviation-grade aluminum, synthetic rubber, had to be imported, often at great cost, and over vast distances. This reality shaped every decision Japanese engineers made. When the Imperial Japanese Navy issued its specification for a new carrier-based fighter in 1937, the requirements reflected this constraint. The aircraft had to be fast, maneuverable, and capable of long-range missions, but it also had to be light, extraordinarily light. The Navy demanded a fighter that could operate from the cramped decks of aircraft carriers, that could fly for hours over the vast expanses of the Pacific without refueling, and that could outturn any opponent in a dogfight. To achieve this, weight became the enemy. Jiro Horikoshi, the chief designer at Mitsubishi, understood the assignment perfectly. He and his team embarked on a ruthless campaign of weight reduction. They used the thinnest aluminum skin that structural integrity would allow. They omitted armor plating for the pilot. They installed fuel tanks without self-sealing liners, a feature American aircraft considered standard because self-sealing materials added weight. Every component was scrutinized, every part refined to its absolute minimum. The result was the A6M0, a masterpiece of minimalist design. It weighed just under 2,000 kilograms empty, half the weight of many contemporary fighters. Its Nakajima Sakae engine, a 14-cylinder radial producing 940 horsepower, was small by international standards, but perfectly suited to the airframe. The Zero could turn tighter than anything in the sky. It could fly over 2,000 kilometers on internal fuel. It could climb to altitude rapidly and maneuver with a grace that seemed almost supernatural. And in the early years of the Pacific War, it dominated. When Zeros swept over Pearl Harbor on December 7, 1941, they encountered American fighters that were slower, less maneuverable, and completely unprepared for the reality of Japanese air power. Over the Philippines, over the Dutch East Indies, over Burma, the Zero carved through Allied defenses with ease. Pilots reported that nothing could turn with it, nothing could escape it. The myth of the Zero became legend. It was the perfect weapon for Japan's lightning war of expansion. But perfection, as the engineers at Saipan were about to learn, is often fragile. The philosophy that created the Zero, lightness above all, maneuverability as the supreme virtue, was born from necessity. Japan's limited industrial base could not produce the kind of massive, overpowered engines that American and British factories churned out. Japanese metallurgy could not match the quality of Western steel alloys. Japanese oil refineries could not produce the high-octane aviation fuel that allowed American engines to run at higher compression ratios and higher power outputs. So Japan built fighters that didn't need those things. Fighters that succeeded through agility, through range, through the skill of their pilots. And, for a time, it worked brilliantly. The Zero's lightness meant vulnerability. A single burst of 50 caliber fire could shred its unarmored structure. Its fuel tanks, without self-sealing protection, ignited easily when struck. Pilots who survived being shot down often described their aircraft disintegrating around them, the thin aluminum skin tearing away in sheets, the wooden wing spars snapping like kindling. And as the war progressed, as American industry fully mobilized, the nature of air combat began to shift. The Americans stopped trying to dogfight Zeros. They developed new tactics that exploited the growing power disparity between their aircraft and Japan's. They attacked from above, diving at high speed, firing a single devastating burst, and then using their superior engine power to climb back to altitude before the Zeros could react. They called it boom and zoom. The P-47 Thunderbolt was the perfect embodiment of this new philosophy. Where the Zero had been designed to minimize weight, the P-47 embraced it. The aircraft weighed nearly 6,000 kilograms empty, 3 times the weight of a Zero. Its wings were thick and sturdy, built to carry heavy bomb loads and withstand the stress of high-speed dives. Its fuselage was armored. The pilot sat behind thick steel plating and bulletproof glass. The fuel tanks were self-sealing, protected by layers of synthetic rubber that swelled when punctured to stop leaks. And at the heart of it all was that engine, the Pratt & Whitney R2800 Double Wasp, 2,000 horsepower. In later variants, with water injection systems that cooled the intake charge and allowed higher boost pressures, the engine could produce 2,300 horsepower. In the experimental P-47M model, built to chase German jets, the uprated R280057 engine generated 2,800 horsepower with war emergency power engaged. 2,800. The number was almost incomprehensible to Japanese engineers. It was 3 times the output of a Zero's engine. It was more power than the combined engines of 2.5 Zeros. It represented an industrial capacity so vast, so overwhelming, that it belonged to a different category of warfare entirely. The Double Wasp was not elegant. Its cylinders were cast iron, not the lightweight aluminum alloy that Japanese engines favored. Its tolerances were loose by Japanese standards, designed for rapid mass production rather than artisanal precision. But it was reliable. It could absorb battle damage and keep running. It could be overhauled in the field by mechanics with basic tools. And most importantly, it could be built by the thousands. By 1944, Pratt & Whitney was producing over 2,000 R2800 engines per month. More than Japan's entire aviation industry could produce in a year across all engine types combined. The factory floors in East Hartford, Connecticut, ran 24 hours a day, staffed by workers who had never built an engine before the war, following simplified assembly procedures that required no specialized training. The engines rolled off the line, were crated, shipped across the Atlantic or the Pacific, and bolted into aircraft that would be flying combat missions within weeks. This was the world the Japanese engineers encountered when they opened that Cowling on Saipan. Not just an engine, not just a machine, but evidence of an industrial system operating on a scale Japan could never match. A system that valued output over artistry, quantity over refinement, and raw power over delicate balance. Standing in the fading light of that July afternoon, Commander Nakamura understood that the war was already over, not tactically, not strategically, but philosophically. Japan had built an air force for the war it wanted to fight. America had built an air force for the war it could afford to fight, and in that difference lay the entire outcome of the Pacific Campaign. The Zero was a work of art, the P-47 was a work of industry, and in total war, industry always wins. The examination of the P-47 at Saipan continued through the night. Commander Nakamura had ordered portable floodlights brought to the airfield, their harsh white glare cutting through the darkness and casting long shadows across the aircraft's battered fuselage. The engineers worked in shifts, measuring, photographing, documenting. Every hour brought new revelations, each more unsettling than the last. Lieutenant Tanaka supervised the disassembly of the engine's accessory section. What they found there challenged everything they thought they understood about American manufacturing. The magnetos were enormous, twice the size of their Japanese equivalents, housed in cast aluminum casings that looked almost crude in their simplicity. Yet, when Tanaka carefully opened one and examined the internal components, he found precision coils wrapped in layers of insulation, contact points machined to tolerances that matched Japanese standards. The carburetor was a massive Stromberg unit, its float chamber large enough to hold nearly 2 liters of fuel. Japanese carburetors were delicate instruments, carefully tuned for optimal fuel-air mixture across different altitudes. This American unit looked agricultural by comparison, its adjustment mechanisms simple and robust. Yet the engineering logic was sound. Large fuel passages meant less restriction, less chance of vapor lock, less sensitivity to combat damage. A bullet hole through a Japanese carburetor meant immediate engine failure. A bullet hole through this Stromberg might reduce power slightly, but the engine would keep running. They moved to the turbocharger installation next, and here the true sophistication of the P-47's design became apparent. The General Electric turbo-supercharger sat in the rear fuselage, connected to the engine by a maze of ducting that ran along both sides of the cockpit. Exhaust gases from the 18 cylinders were collected and channeled back through thick steel pipes to spin the turbine at speeds exceeding 20,000 revolutions per minute. The compressed air then flowed forward through an intercooler that used ram air to reduce its temperature before feeding it into the engine's intake. It was a system of staggering complexity, requiring precise coordination between multiple components operating under extreme conditions. Japanese engineers had experimented with turbocharging but had never achieved reliable results. The extreme heat, the vibration, the need for exotic high-temperature materials, all of it had proven too difficult for Japan's industrial base to mass-produce. Yet here it was, installed in what the Americans considered a standard production fighter, not a prototype, not an experimental aircraft. A mass-produced machine built by the thousands, each one equipped with a turbocharger system that Japan's best laboratories couldn't replicate. Nakamura studied the installation for nearly an hour, his notebook filling with sketches and calculations. The turbocharger allowed the R-2800 to maintain its sea-level power output at altitudes where Japanese engines were gasping for air. At 25,000 feet, a Zero's Sakai engine produced perhaps 600 horsepower, struggling in the thin atmosphere. The P-47's double Wasp, fed by compressed air from the turbocharger, still generated over 1,800 horsepower. The implications for combat were devastating. American pilots could cruise at altitudes where Japanese fighters barely functioned, then dive down with enormous speed advantages, attack, and climb back up before the Zeros could respond. It wasn't just superior power, it was superior power at altitude, where the Pacific Air War was increasingly being fought. As dawn broke over Saipan, the engineers turned their attention to the aircraft's structure. They removed inspection panels to examine the internal framework, and what they found was equally instructive. The P-47's wing was built around a massive main spar, a single forged aluminum beam that ran from tip to tip through the fuselage. It was over 20 centimeters deep at its thickest point, engineered to withstand loads that would have torn a Zero's wing clean off. The wing skin itself was thick, nearly 2 millimeters in, places where a Zero's skin measured less than 1 millimeter. Beneath the skin, a dense network of ribs and stringers provided additional strength. The entire structure was designed to tolerate battle damage, to absorb punishment, and keep flying. Weight was not an enemy here. Weight was armor. Weight was survival. They measured the fuel system next. The P-47 carried over 1,300 liters of fuel internally, nearly double what a Zero could hold, and all of it was stored in self-sealing tanks, each one lined with multiple layers of synthetic rubber compound that swelled when exposed to fuel, automatically sealing bullet holes. Japanese pilots had learned to dread the bright flash that meant their fuel tank had been hit. American pilots in P-47 seconds often flew home with tanks riddled with holes, the self-sealing system doing its job silently and effectively. The armament inspection came next, and here the difference in philosophy was most stark. The P-47 carried 8 Browning M250 caliber machine guns, 4 in each wing. Each gun had a magazine capacity of 400 rounds, giving the aircraft 3,200 rounds of total ammunition. The firepower was immense, concentrated in a cone of destruction that could saw a fighter in half or shred a bomber's fuselage in seconds. By comparison, the Zero carried 2 7.7mm machine guns and 2 20mm cannon with limited ammunition. The cannon were powerful, certainly, capable of destroying targets with a single hit. But they fired slowly, only 100 rounds per minute, and carried just 60 rounds per gun. 3 seconds of firing and the cannon were empty. The P-47 pilot could hold his trigger for 40 seconds of continuous fire before running out of ammunition. Lieutenant Tanaka performed the calculation. 8 guns, firing at a combined rate of 9,600 rounds per minute. That meant 160 rounds per second striking the target. Even if only 10% of those rounds hit, It was still 1650 caliber bullets impacting per second. No aircraft, no matter how maneuverable, could survive more than a moment under such concentrated fire. The Americans had taken the philosophy of overwhelming force and applied it to individual aircraft. Where Japanese design sought efficiency, American design sought redundancy. Where Japan built fighters to succeed through skill, America built fighters to succeed through sheer material advantage. As the sun climbed higher and the tropical heat returned, Commander Nakamura ordered his team to compile their findings. The report would fill dozens of pages, but the conclusion could be summarized in a single devastating sentence. The P-47 Thunderbolt represented an industrial and engineering capability that Japan could not match, could not counter, and most importantly had not even understood existed until now. That afternoon, as the engineers prepared to move on to examine the other captured aircraft, Nakamura stood alone beside the P-47. He placed his hand on the cowling one final time, feeling the heat radiating from the metal under the sun. In his mind, he was already writing the confidential assessment that would accompany the technical report. This aircraft, he would write, is not designed to win through superiority of design or elegance of execution. It is designed to win through superiority of resources. Every component reflects a manufacturing philosophy predicated on abundance, abundant materials, abundant fuel, abundant industrial capacity. Japan cannot compete on these terms. Our fighters are products of scarcity, engineered to extract maximum performance from minimum resources. Theirs are products of plenty, engineered to survive, to overpower, and to be replaced when lost. He would not write what he truly thought, what kept him awake that night in his tent. That Japan had built an air force to fight a romantic war of skill and courage, while America had built an air force to fight an industrial war of attrition and arithmetic. And in such a war, all the skill and courage in the world could not overcome the simple mathematics of 2,800 horsepower versus 940, of 8 guns versus 4, of thousands of aircraft versus hundreds. The P-47 was not just an aircraft. It was a message, written in aluminum and steel, and forged into a shape that could fly. And the message was simple. America would win not because its pilots were better or its tactics superior, but because it could build more, faster, and with power to spare. Standing there in the ruins of Saipan, surrounded by the wreckage of Japan's defensive perimeter, Commander Nakamura finally understood what his nation was truly fighting against. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical report from Saipan reached Tokyo 3 weeks later, traveling by submarine through waters now patrolled by American destroyers and aircraft. It arrived at the Koku Gijutsu-sho headquarters in a sealed diplomatic pouch, marked with red stamps indicating highest priority material. Commander Nakamura's assessment, along with hundreds of photographs and detailed technical drawings, was distributed to senior engineers across Japan's aviation industry. The response was silence. Not the silence of shock or disbelief, but something worse, the silence of confirmation. Because the truth was, by mid-1944, Japan's aviation establishment had already begun to suspect what Nakamura's report now confirmed. The signs had been accumulating for months. Combat reports from the Marianas, from Rabaul, from New Guinea, all told the same story. American fighters were growing more powerful, more numerous, and more difficult to defeat. Japanese pilots who had survived encounters with P-47 seconds described aircraft that could dive away from any XPATE engagement, that could absorb catastrophic damage and keep fighting, that could climb back to altitude with a speed that seemed impossible. At Mitsubishi's design bureau in Nagoya, Chief Engineer Jiro Horikoshi read Nakamura's report with a mixture of admiration and despair. He recognized the R-2800 engine from intelligence reports. He had seen the specifications, had understood in abstract terms what 2,800 horsepower meant, but seeing it described in such detail, seeing the photographs of the massive radial engine filling the P-47's cowling, seeing the measurements and calculations, it made the reality inescapable. Horikoshi had spent the past year attempting to develop a successor to the Zero, an aircraft designated the A-7M Repu that would match American performance. But every design iteration ran into the same fundamental constraint: engines. Japan's most powerful production engine, the Mitsubishi Kinsei, produced 1,800 horsepower when everything went right, which it rarely did. The engine was temperamental, prone to overheating, and in desperately short supply. Even if the Repu could be perfected, even if it could match a P-47 inches performance, Japan could build perhaps 50 per month. America was producing 500 P-47 seconds per month. 500. The number haunted Horikoshi. It appeared in every production report, every intelligence assessment, every strategic analysis. American aircraft production had reached levels that seemed divorced from physical reality. In 1944 alone, the United States would manufacture over 96,000 aircraft. Japan would manage 28,000, and most of those would be trainers and obsolete designs pressed into service out of desperation. But it was the engine production figures that truly revealed the scale of the disparity. Pratt & Whitney alone was producing more engines per month than Japan's entire aviation industry combined, and each of those engines was more powerful, more reliable, and more sophisticated than anything Japanese factories could manufacture. The report from Saipan was forwarded to the Naval General Staff, where it landed on the desk of Admiral Takejiro Onishi, one of the architects of Japan's carrier aviation strategy. Onishi had been a proponent of the Zero's design philosophy, had championed the emphasis on range and maneuverability over protection and firepower. He had believed that superior pilot training and tactical doctrine could overcome material disadvantages. He read Nakamura's report 3 times, each reading more difficult than the last. The section on engine power was particularly painful. 2,800 horsepower. The phrase appeared again and again throughout the document, always with the same implicit comparison. 3 times what a Zero could produce. 3 times, not 30% more, not 50% more. 3 times. Onishi performed his own calculation, one that Nakamura had been too diplomatic to include in the official report. If a P-47 had an engine 3 times as powerful as a Zero, and if America was building 500 P-47 seconds per month while Japan managed to build perhaps 100 Zeros, then America was adding the equivalent of 1,500 Zeros' worth of engine power to the Pacific theater every month. 1,500, against Japan's 100. A 15-to-1 advantage in raw mechanical force, and that was just one American fighter type. The mathematics of defeat were becoming impossible to ignore. At the Nakajima Aircraft Company, engineers were conducting their own analysis of the P-47's turbocharger system. They had obtained copies of the Saipan photographs and were attempting to reverse engineer the General Electric installation. The complexity was daunting. The turbocharger alone required precision steel alloys that Japan could no longer reliably produce. The ball bearings that allowed the turbine to spin at 20,000 revolutions per minute were beyond Japanese manufacturing capability without imported materials that were no longer available due to the American submarine blockade. But what troubled the Nakajima engineers most was not the technical challenge. It was the realization that America had solved these problems years ago, had integrated turbochargers into production fighters as early as 1942, and had been steadily refining and improving the technology ever since. Japan was attempting to catch up to a target that kept accelerating away. In September 1944, 3 months after the Saipan examination, a second captured P-47 was recovered from Guam. This one was a later D-model variant with the bubble canopy, and it was in remarkably good condition. Its pilot had made a forced landing after running out of fuel. The aircraft was carefully disassembled and shipped to the Tachikawa Air Arsenal outside Tokyo for detailed analysis. The team that examined this second aircraft included some of Japan's most senior aviation engineers. They spent 6 weeks measuring every component, testing materials, analyzing the construction techniques. Their report, completed in November, was even more sobering than Nakamura's. The metallurgical analysis revealed that the P-47 used aluminum alloys of superior quality to anything Japan could produce. The steel in the landing gear was harder and more fatigue-resistant. The synthetic rubber in the fuel tank liners was more effective at sealing punctures. Even the paint applied to the aircraft's skin was more durable, more resistant to the harsh tropical environment. Every detail pointed to the same conclusion. America's industrial base had achieved a level of sophistication that Japan could not replicate. Not because Japanese engineers were less capable, but because the infrastructure required the steel mills, the chemical plants, the machine tool factories. The electrical power grid simply didn't exist on the necessary scale. The report included a particularly devastating section on production methods. By examining the rivet patterns and assembly marks, the engineers had reconstructed how the P-47 was manufactured. The entire aircraft was built in sub-assemblies by workers with minimal training, following standardized procedures that allowed rapid production. Parts were interchangeable between aircraft. Components could be swapped in the field without custom fitting. The entire philosophy was predicated on volume production and ease of maintenance. Japan's aircraft were still being built more like custom automobiles than mass-produced machines. Skilled workers, hand-fitted components. Final assembly required experienced craftsmen. Repairs often demanded factory support. The Zero had been designed for a world where each aircraft was precious, where conservation of resources was paramount. The P-47 had been designed for a world where aircraft were expendable, where losses could be rapidly replaced, where the limiting factor was not industrial capacity, but how fast pilots could be trained. By late 1944, the truth was inescapable. The discovery of what lay inside that P-47 Cowling 2,800 horsepower of American industrial might was not so much a revelation as a confirmation of what Japan's leadership had feared, but refused to fully acknowledge. The Pacific War was not being decided by tactical brilliance or warrior spirit. It was being decided by production charts, by horsepower ratings, by the simple, brutal arithmetic of industrial warfare. And in that arithmetic, Japan had already lost. The captured P-47 at Tachikawa was destroyed in an American bombing raid in February 1945. The facility burned for 3 days, consuming not just the aircraft but also the detailed technical reports, the photographs, and most of the measurements the engineers had so painstakingly compiled. In the chaos of Japan's final months, few people noticed. The information had already been distributed to those who needed it, and by then, it hardly mattered. The war had moved beyond analysis. It had entered its final, desperate phase. By the time Tokyo fell silent in August 1945, the Pacific Theater had become a demonstration of exactly what Commander Nakamura had foreseen on that humid afternoon at Saipan. American industrial power, embodied in aircraft like the P-47 Thunderbolt, had overwhelmed Japan through sheer material superiority. The numbers told the story more clearly than any strategic analysis could. The United States produced over 15,000 P-47 Thunderbolts during the war. 15,000. Each one powered by an R-2000, 800 engine that outclassed Japanese fighters by a factor of 3. Each one armed with 850 caliber machine guns, capable of absorbing punishment that would have disintegrated a Zero. Each one a testament to an industrial philosophy that Japan could neither match nor counter. In the final year of the war, P-47 seconds flew ground attack missions across the Pacific, their massive engines allowing them to carry bomb loads that exceeded many medium bombers. They escorted B-29 superfortresses to the Japanese home islands, their turbochargers enabling them to operate at altitudes where Japanese interceptors struggled to reach. They destroyed thousands of trucks, trains, ships, and aircraft on the ground and in the air. Their loss rate was among the lowest of any American fighter, not because they avoided combat, but because their robust construction allowed them to survive damage that would have been fatal to lighter aircraft. Japanese pilots came to dread encountering P-47 seconds. The aircraft's nickname among American crews was the Jug, short for juggernaut, an unstoppable force. Japanese pilots used different terms, most of them untranslatable, all of them conveying the same sense of helplessness. You could hit a P-47. You could damage it. But unless you destroyed it immediately, it would simply dive away, its powerful engine carrying it to safety at speeds no Japanese fighter could match. The few Japanese aces who survived the war to write memoirs spoke of the P-47 with a mixture of respect and frustration. It was not the most maneuverable American fighter. That distinction belonged to the lighter P-51 Mustang. It was not the most elegant. The Navy's F-4U Corsair was more graceful. But it was the most intimidating because it represented something beyond tactical considerations. It represented the full weight of American industrial might, compressed into a single-seat fighter and sent aloft by 2,800 horses of mechanical fury. Commander Saburo Nakamura survived the war. He was among the technical experts who met with American occupation officials in the months after surrender, providing information about Japanese aviation development. In one of these meetings, held in November 1945, an American intelligence officer asked him when he had first realized Japan would lose the air war. Nakamura's answer was immediate. "The moment we opened the cowling of that P-47 on Saipan." The officer pressed for details. Nakamura explained about the engine, about the horsepower, about the industrial capacity required to manufacture such machines by the thousands. He spoke about the turbocharger, about the armament, about the fundamental difference in design philosophy. The American officer, a technical specialist himself, understood immediately. He later wrote in his report, "The Japanese engineer seemed almost relieved to finally explain to someone who would understand. He said they had built fighters for the war they could afford to fight. We had built fighters for the war we could afford to win." The difference was everything. In the years after the war, the story of the P-47's engine became part of the larger narrative of American industrial dominance. The R-2800 Double Wasp continued in production until 1950, eventually powering everything from fighters to transport aircraft to helicopters. Over 125,000 R-2800 engines were manufactured in total, making it one of the most successful aircraft engines in history. Pratt & Whitney's engineers, when told about the Japanese reaction to discovering the engine's power output, expressed surprise. To them, 2,800 horsepower was merely adequate, a necessary figure to meet performance requirements. They had already been working on more powerful engines, designs that would exceed 4,000 horsepower. The R-2800 was not considered exceptional within the American industry. It was simply what the mission required. That perspective, more than any single technical specification, captures the essence of what the Japanese engineers discovered at Saipan. America had not strained to create the P-47. It had not pushed the boundaries of what was possible. It had simply designed an aircraft to meet operational requirements, then manufactured it at scale using established industrial processes. The P-47 was not a miracle of engineering. It was a product of capacity. For Japan, the lesson came too late. The nation's aviation industry spent the final years of the war attempting to develop fighters that could compete with American designs, but the effort was doomed by resource shortages, production bottlenecks, and the relentless American bombing campaign. Aircraft like the Ki-84 Hayate showed promise, but could not be manufactured in sufficient numbers. The Ki-100, developed by mating a radial engine to an existing airframe, was arguably superior to the P-47 inches, certain respects, but only 500 were built before the war ended. 500. Against America's 15,000 P-47 seconds, against the total American production of 96,000 aircraft in 1944 alone, the numbers rendered tactical discussions meaningless. Lieutenant Hiroshi Tanaka, the young engineer who had first read the data plate on the R-2800, spent the post-war years working in Japan's commercial aviation industry. He rarely spoke about his wartime experiences, but in a private journal discovered after his death in 1987, he wrote about that day at Saipan in detail. "We understood in that moment," he wrote, "that we had been fighting with weapons from one era against weapons from another. Not because American technology was more advanced, though in many ways it was, but because American industry could implement that technology at scale. A brilliant design that can only be built in small numbers is merely an interesting footnote. A competent design that can be built by the thousands wins wars. The P-47 taught us that truth. The legacy of that lesson extended beyond aviation. In the post-war period, Japan's reconstruction focused heavily on developing industrial capacity, on building the infrastructure that could support mass production of high-quality goods. The engineers who had examined captured American aircraft during the war applied those lessons to cars, to electronics, to shipbuilding. They studied American manufacturing techniques, American approaches to quality control and standardization, American methods of organizing production lines. By the 1970s, Japan had become an industrial powerhouse, exporting high-quality products around the world. The irony was not lost on those who remembered. Japan had learned the lesson the P-47 taught, had absorbed the philosophy that power comes not from perfection, but from the ability to produce excellence at scale. In 1994, 50 years after the examination at Saipan, a group of surviving Japanese aviation engineers held a private memorial ceremony. They gathered at a museum that housed a restored P-47D, one of the few preserved in Japan. The aircraft sat in pristine condition, its silver aluminum skin gleaming under museum lights, the massive R-2800 engine visible through a cutaway panel in the cowling. The engineers, now elderly men in their 70s and 80s, stood before the aircraft in silence. One of them, a former Nakajima Company engineer named Kenji Matsumoto, finally spoke. "We built beautiful aircraft," he said quietly. "The Zero was a work of art, a perfect expression of our capabilities, but art does not win wars. This machine," he gestured at the P-47, "was not art, it was industry, it was capacity. It was 2,800 horsepower saying, 'We have so much power we can waste it on a single fighter.' That was the message we failed to understand until too late." Another engineer, one of Commander Nakamura's former team members, added, "The Americans did not beat us with better pilots or better tactics. They beat us with mathematics, with production numbers, with engines that produced 3 times our power and could be built by the thousands. You cannot outfight mathematics." They stood there for another hour, discussing technical details, sharing memories, occasionally laughing at the absurdity of how young they had been, how confident they had felt before Saipan. Before they truly understood what they were facing, before they opened that cowling and saw the future, the P-47 Thunderbolt was retired from American service in 1953, replaced by jet fighters that rendered even its impressive performance obsolete. But its legacy persisted. The aircraft had demonstrated that in modern warfare, the capacity to produce reliable, powerful machines at industrial scale was more decisive than any single technical innovation. It had shown that durability and firepower could compensate for lack of agility. It had proven that survival often mattered more than elegance, and at the heart of it all was that engine. The Pratt & Whitney R2800 Double Wasp, 18 cylinders of American industrial might. 2 rows of 9 cylinders each, displacing 46 litres, producing 2,800 horsepower when, pushed to war emergency power, enough power to equal nearly 3 Japanese fighters, enough power to change the course of air battles, enough power to represent the difference between 2 industrial philosophies, 2 approaches to warfare, 2 nations' fates. The Japanese engineers who first saw that engine on Saipan in July 1944 had witnessed more than a piece of machinery. They had witnessed the physical embodiment of why their nation would lose the war, not because they lacked courage or skill or intelligence, but because they lacked the one thing that mattered most in industrial warfare, the capacity to produce overwhelming force and sustain it over time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.